So a refrigerator, in its most general sense, would be a device that takes some input work and uses that to transport heat from one place to another one. And if it does this cyclically, we can sustain a region of space that is colder than the ambient temperature, and in return, we would heat up some other region. So the widespread technology to achieve this objective has been vapor compression cycles. They use a fluid refrigerant, which undergoes a phase transition from a liquid to a gas, and in that evaporation stage, it steals the latent heat from the environment, and then we can condense this refrigerant elsewhere to reject that heat. So the alternative refrigeration systems, they aim to substitute this phase transition for one of another kind. And in our specific case, it would be a magnetocaloric phase transition. This happens in materials that they go from a ferromagnetic to a paramagnetic state. And ferromagnets are characterized by having the dipolar magnetic moments of the particles or molecules that compose it aligning to a particular direction, which gives them a net magnetization. So if we go increasing the temperature of a ferromagnet past its transition temperature, called the Curie temperature, we end up in a paramagnetic state where the thermal excitations of those molecules or particles, they destroy the magnetic order that we saw before. However, if we apply an external magnetic field to a paramagnet, we force it to come back again to a ferromagnetic state, and thus we will be lowering the entropy associated to the magnetic ordering of the material. And if the environment is adiabatic, well, the excess thermal entropy would raise the temperature of the material. So effectively what we have done here has been to substitute pressure and volume as thermodynamic variables of the cycle for applied magnetic field and magnetization. However, the question still remains, why would we go through the effort of designing a machine that would exploit this particular phase transition? Well, magnetocaloric materials are solid, which means that they do not leak. And in comparison to vapor compression cycles, they use fluid refrigerants that are ozone depleting substances like hydrochlorofluorocarbons and other halogen gases. So this is a bigger issue in vapor compression cycles. They also have compression and expansion stages, which means that they're pretty noisy, and these processes are far from being isentropic, in comparison to magnetocaloric materials, which many have proven to have a practically reversible phase transition. So the most commonly used magnetocaloric material in prototypes has been gadolinium metal, which is an element of the periodic table in the group of lanthanides, and it has been used for this purpose because it has a transition temperature that is close to the ambient one. So we know the magnetization of gadolinium for a given internal magnetic field and temperature, and from there we can calculate the change in magnetic entropy of gadolinium. So broadly speaking, magnetocaloric materials are classified in two kinds, first order and second order, and gadolinium would be of the second order, which means that the slope of its magnetization around the transition temperature is smoother than in first order cases, and that is translated into a lower maximum magnetic entropy change, but we would see the magnetocaloric effect present at a wider range of temperatures. Many numerical models have chosen to represent the magnetization of its magnetocaloric materials through an analytical model called the mean field theory. This is quite versatile because it can represent many different magnetocaloric materials. However, it has some implicit assumptions that makes sometimes the calculus of the adiabatic temperature change have some discrepancies with the experimentally measured data. And for that reason, I chose to use experimentally measured data for the magnetization of gadolinium to represent the magnetocaloric effect or the adiabatic temperature change of the material. So I've talked about the potential of magnetic refrigeration. However, it certainly has its limitations, and the main one would be the low adiabatic temperature change of magnetocaloric materials. For gadolinium, as we have seen in the last slide, and with an applied field of 2 teslas, which is a pretty strong magnetic field, the maximum adiabatic temperature change would be about 5.5 kelvins. And that would be all we have to transfer the heat from the solid phase to a heat transfer fluid, and then we'll move that heat around. Then there is the cost of magnetocaloric materials and the neodymium of the permanent magnets we need in our machine. They're both made of rare earth materials, which increase the capital cost of the machine. So 5 kelvins is not a temperature span that is useful for our daily application. So engineers have changed several of these thermodynamic cycles, one after the other one, to attain temperature spans that are more useful. And this has been done through the means of regeneration. A regenerator, in its most general sense, is a device that absorbs and releases heat to link two thermodynamic cycles together. And in our specific case, the magnetocaloric material is at the same time the refrigerant and the regenerator. And that's why we call these devices Active Magnetic Regenerators, or AMR for short. So the regenerator has the magnetocaloric material arranged in a porous structure, and And in a steady state operation, it represents a temperature span between the cold sides and hot sides of the machine. And it is in this temperature span where we see blurred in all the thermodynamic cycles together. As you can see in the left side of the slide, I've depicted the thermodynamic cycles of the most extreme points of the regenerator in orange, and well, the green shadow would represent all the thermodynamic cycles that are in between. So the main elements of a magnetic refrigerator would be the following: the active magnetic regenerator, a magnet that magnetizes our regenerator, two heat exchangers at the cold side and hot sides of the machine, and a pump that moves the heat transfer fluid around to link all the thermodynamic cycles and the heat exchangers together. So most prototypes have chosen to follow a Brayton-like thermodynamic cycle, which means as fast as possible magnetization and demagnetization stages, and that is to keep as high as possible temperature gradient between the solid and fluid phases of the regenerator for a faster heat transfer. And that would mean that we could increase the operational frequency of our machine and pump heat at a higher rate. So the stages of the thermodynamic cycle would be the following. First, fast magnetization, then we would send up the heat transfer fluid to the heat sink, then demagnetization, regenerator cools down, and then we can send the heat transfer fluid to the cold source. Prototypes have shown two main geometries in their regenerators and have been a stack of parallel plates and randomly packed beds of particles. We can classify prototypes into kinds as well. That would be linear and rotatory. Linear ones have the regenerator or a magnet move reciprocatively along a line, and that would mean that we have to accelerate and decelerate a mass several times per cycle, which brings high mechanical losses to the system. However, they're simpler to build, so they can be useful for experiments and other kinds of demonstrations. Rotatory types, though, have a wheel in which regenerators are placed along its circumference, and that wheel of regenerators or a wheel of magnets spins relatively to each other along the same rotational axis. So the spinning element acts like a flywheel, and that lets us operate the machine at a much higher frequencies with not so many mechanical losses. However, they require a much more complicated valve system to time very well the fluid surges in the thermodynamic cycle. Another way of investigating the dynamics of magnetic regenerators would be through numerical modeling. These are much less expensive to build than prototypes. However, their solution relies on the hypothesis and models we choose for them. So we have to check that the solution is really physical. So at minimum, we have to solve the energy equations for the solid and for the fluid domain too, because well, it's the substance that links all the thermodynamic cycles and the heat exchangers together. And if we apply the conservation of energy to these two domains, we would get the following partial differential equations. And they both have in common the temporal change and the diffusion terms. And well, the solid domain has to include a source term expressing the magnetocaloric effect, which changes according to changes in the internal magnetic field. The fluid domain also has the convection term, which represents the transport of temperature. And from the coupled solution of these two equations, we will get the temperature field in the regenerator at any point in time and space. And by integrating that, we would get more interesting values like the coefficient of performance, the cooling power, or the input work of the regenerator. Most of the numerical models presented in the literature are one-dimensional, which means that they only solve the dimension that links the cold and hot heat exchangers together. And the other two spatial dimensions are considered to be homogeneous. Because we cannot explicitly model the heat transfer between solid and fluid phases in one-dimensional models, it requires an additional term to express that heat exchange, and that would be modeled by the Nusselt number. The Nusselt number is calculated as you see on the left corner of this slide, and right next to it there is a color image which represents the value of the Nusselt number for a forced convection simulation of a two-dimensional pack of cylinders that started with an initial temperature gradient in the direction of the flow. So I showed you this image to give you an idea in which kind of error we would incur in if we assume a constant average Nusselt number for our geometry, and that is what is usually done for one-dimensional numerical models. I show you here two examples too, one for randomly packed beds of particles. Wakao and Keiwei in their book they compile several of these correlations for the Nusselt number for different kinds of packed beds, and they fitted a function through them to get a unified expression for the correlation of the Nusselt number for these packed beds. And For parallel plates, Rosenau et al. In their book, they presented correlations for the Nusselt number, not only depending on the geometry of those rectangular channels, but also for different kinds of boundary conditions. They presented one was in red for a uniform temperature at the walls, and another one in green for a uniform wall heat flux at the walls. And well, this gives us an idea of how many variables influence the value of an average Nusselt number, that it ends up not being constant neither through space nor time. Then, when modeling the magnetic field in our regenerator, we should keep in mind three different physical fields. B would be the magnetic flux, which is the variable which obeys the law of continuity you see on the right corner of the slide, and is the summation of the other two fields, H and M. M would be the magnetization of the material, which is the magnetic field created by the sample itself, and H would be the magnetic field intensity, which is the magnetic field created by other kinds of boundary conditions. So the internal magnetic field is different from the applied one because of the magnetization of the sample, and this is approximated via the magnetizing field that is usually taken proportional to the magnetization of the sample, and is heavily dependent on the geometry of the sample itself. This approximation comes from the case where this is exactly true, and that would be for ellipsoids of constant magnetization under a uniformly applied magnetic field. And that is another aspect of modeling the magnetic field, that the applied field is never uniform. That can be approximated as well by resolving a simplified magnetic circuit between the poles of the magnet. So we would calculate the reluctances of the materials that are between the poles, and then we would solve a magnetic circuit that is an analogous concept to the electrical circuit, so the effective magnetic field on the sample would be analogous to a voltage. We also have to approximate the input work we are investing in moving the heat transfer fluid around. And well, this is one of the easier phenomena to model because we generally have a laminar flow of low Reynolds number. And well, for the case of parallel plates, we can obtain analytically the solution of the fluid velocity profiles, and so the expression of the friction factor is quite direct. But for other cases, like for randomly packed beds of particles, the expression of the friction factor is a bit more complicated, so we are limited by the geometries that have previously been studied. On top of the physical phenomena to model, I also identified two physical parameters that change substantially in the ranges of temperature and applied magnetic field that we usually see in magnetic regenerators. And first one would be the viscosity of the heat transfer fluid. Most prototypes use a water-based heat transfer fluid, and well, in the ranges between 0 and 30 degrees Celsius, we can see on the left graph how the dynamic viscosity of water changes more than 100% between those values. This means that the Reynolds number could double from point to point in the regenerator, and that could change the shape of the velocity profiles and thus the convective heat transfer properties. There's also the magnetic relative permeability of gadolinium in the ferromagnetic region. It changes quite a bit between 0 and 2 Teslas, and that might change the ratio between the internal and applied magnetic field, especially for the cases where the demagnetization is rather high. On this slide, you can see a summary of the latest numerical models for magnetic regenerators, and you can see there is a good mixture between the cases where they chose the mean field theory and measurements to represent the magnetization for the calculus of the magnetocaloric effect, and well, half of them are one-dimensional models, and most of them they chose not to solve the magnetic field that the regenerator would perceive. They chose to apply a uniform internal magnetic field or to approximate the magnetizing field. There are two three-dimensional models, one from Bouchard et al., which solve all the phenomena involved, and well, its calculations were so detailed that the computational domain was quite reduced. Then Cameron et al. Also published a three-dimensional model, but they chose not to solve the magnetic field. So to familiarize myself with the numerical modeling of these systems, I started by constructing a one-dimensional numerical model. And so I discretized the following partial differential equations you see on the left corner by the Crank-Nicholson finite difference scheme, which is second-order accurate and unconditionally stable. And this particular set of equations gave me a three-diagonal linear matrix to be solved, which is great because it can be solved through a direct method. The numerical experiments revolved around the regenerator of Tusek et al. That you see on the left side of the slide. And well, in terms of the Nusselt number, most publications they do not specify a different Nusselt number between the surge stages and the demagnetization stages. I thought it would be more accurate to represent the heat transfer between phases just solely by the thermal conductivity of the heat transfer fluid on the demagnetization stages, since the heat transfer fluid is at rest. And I also solved the simplified magnetic circuit between the poles of the magnet, and that gave me a nonlinear equation to be solved at every time step. On this slide, you can see the solution of the regenerator, so the temperature span of the regenerator at zero cooling load, and it's plotted against the utilization ratio, which is a ratio between the heat capacity of the heat transfer fluid that is entering the regenerator divided against the heat capacity of the solid phase. So this variable gives us an idea of how much heat are we evacuating from the regenerator. So first four lines would represent the solution of a one-dimensional model by Engelbrecht et al. And well, first one would be without any loss mechanisms. Second one taking into account the demagnetization field. Third one would be taking into account the demagnetization and heat losses, and the heat losses were approximated throughout all the geometry of the regenerator and then lumped into the cold heat exchanger as a load. Fourth one would be taking into account only maldistribution losses, which are losses associated to the manufacturing process of the regenerator, so differences in the plate spacings and thickness of the plates, which would create a non-uniform velocity profiles. And models number 5 and 6 would be the model I presented you earlier. Number 5 with no losses, and 6 solving the simplified magnetic circuit. So it is number 6 that is closest to the experimental measurements from Tusek et al. So we could assume that this would behave as a real regenerator, especially because I'm not going to change the operational point. So the numerical experiments that I performed with that one-dimensional solver consisted on introducing insulator layers along the length of the regenerator to try to stop the conduction losses from happening, all while keeping the mass of the magnetocaloric material constant. So on the left graph you can see what happens when we go increasing the number of insulator layers. The maximum temperature span increases, especially at lower utilization ratios where the conduction terms are more important than the convection ones. And on the graph on the right you can see what happens when we go increasing the length on those insulator layers. The temperature span of the machine increases, especially at higher utilization ratios. And this happens not only because we are increasing the length of the regenerator, but also because I didn't take into account the heat capacity of those insulator layers in the expression of the utilization ratio. And so the curves of the temperature span of the machine get wider and the regenerator is more useful at higher utilization ratios. Then I went on to calculate the generated entropy in the regenerator, and this is a very useful concept because it lets us quantify what are the inefficiencies of our machine. So starting from the solid conduction, we can see how it dips every time we insert one of those insulator layers. And well, as we see in the temperature profile on the right, those insulator layers hold an increased amount of the temperature gradient of the regenerator. And as a consequence, well, the temperature gradient of the magnetocaloric material is reduced. And because of that increased temperature gradients that are held by the insulator layers, we see those spikes in the generated entropy by fluid conduction. This is because some of the heat that was being stopped by those insulator layers is being bypassed through the heat transfer fluid. So when we check the generated entropy by convection, we see those spikes again, and that would be for the same reason, right? Because the heat transfer fluid is encountering those increased temperature gradients of the insulator layers. However, around the last insulator, we can see a generalized increase of the generated entropy by convection, and that would be because the last layer is working around the Curie temperature, and by reducing the gradient of the magnetocaloric material, we bring more points to work around the Curie temperature, and thus we increase the magnetocaloric effect in our regenerator. So that would be a positive effect. And then finally we have the generated entropy by viscous action, and that would increase because of the regenerator working at a larger temperature span, so we would have more points working at a lower temperature, which means higher viscosity for the heat transfer fluid. So the next step in the project was to produce a numerical model that would be as reliable as possible, and for that I chose to stay as close as possible to the direct numerical resolution of the physical phenomena involved in the regenerator. And so I went on to code the solvers in the OpenFOAM framework, which is commonly known for being a library related to computational fluid dynamics. However, I would say that it's much more than that. It's a mathematical tool that lets us operate and manipulate between physical fields, including the resolution of partial differential equations. It is coded in C++, which makes the whole structure very modular. And well, the discretization of those partial differential equations is done by the finite volume method. It's a method that is similar to the finite element one, only that the solution is stored at the center of the cells. So when computing the flux between two neighboring cells, there is only a single value, which makes the whole method implicitly conservative. We can build two-dimensional or three-dimensional models, and well, as you can see there, the syntax of those partial differential equations is pretty straightforward. It also includes some software to discretize our geometries, and we can use also a third-party solver called CFMesh that is pretty useful for a little bit more challenging geometries. So to be sure that I was able to compute the thermodynamic cycle of magnetic refrigerators, I went on to validate one by one the physical phenomena that are present in our regenerator. So I started with the toughest geometry I could think of, and that would be randomly packed beds of particles. And so I developed a script in Blender to generate these geometries, and well, the result you can see in the lower left side of the slide. On the right side of the slide, you can see the distribution of porosity along the radius of those packings, starting from the outside and then going to the inside. And the color of the lines would represent different mesh sizes. And in the cases where the solution is converged, you can see how it is pretty close to the experimental measurements of Guilles et al. So then I went on to simulate the fluid flow through those packed beds, and the graphs now represent the normalized fluid velocity profiles of those packings, and the lines represent again different cell sizes. And in all cases, the results are pretty close to the experimental measurements again. And well, this was solved through the native solver Simple Foam. I chose numerical schemes that were second order accurate. The meshes were around 10 million, and it was running about 100 CPUs. This slide is similar to the last one in that I show you again the normalized fluid velocity profiles of those packings, except this time the colored lines represent different Reynolds numbers. And well, I produced these figures because I wanted to show you how, even though we change substantially the Reynolds number, well, the fluid velocity profiles do not change substantially, and thus differences in the dynamic viscosity of the fluid flow would not change the convective heat transfer properties, and we can pre-calculate the fluid velocity field before the thermodynamic cycles, which is very beneficial because we can save a lot of computational time. Then I had to prove that I could solve correctly the conjugated heat transfer problem, and for that I chose to compare the solution of my solver to a benchmark provided by Ramsack, which consisted in the direct numerical simulation of backward step flow, which had a solid slab at the lower part, and then that solid slab was heated at the bottom at a dimensional temperature of 1. So the flow is entering the backward step flow with a dimensional temperature of 0, and well, it has a very well defined separation and reattachment point of the flow. So after doing the grid sensitivity analysis in the middle of the first separation, you can see the solutions on the right side of the slide. On the top for the adimensional temperature and at the bottom for the Nusselt number, both at the interface between the solid and fluid domains. And while the different lines would represent different ratios for the solid thermal conductivity and the fluid thermal conductivities. And in all cases, well, it's pretty close to the benchmark provided by Ramsack. Finally, I had to prove the correct resolution of the magnetic field, and since there is no electrical fields involved in this problem, it is only necessary to solve the continuity of the magnetic flux. And well, at the same time, since there's no electrical fields, we can express the magnetic field intensity by a gradient of magnetic scalar potential, and that would lead us to that Laplacian equation you see there on the red square that is multiplied by the magnetic relative permeability of the medium. And well, I chose a case that would have an analytical solution by the Biot and Savart law, and it consisted of that bar magnet you see there with a constant remanent magnetization. And on the right side of the slide, you can see a graph. There you can see how, as we go decreasing the cell size at the surface, we go approaching the discontinuity that is present at the corner of that bar magnet. So after I show you how we can accurately calculate the different physical phenomena in the regenerator, I show you the flowchart which would calculate the thermodynamic cycle of the regenerator. And we would start every time step by reading the fluid flow from a file. And that would be because we have proved that the fluid velocity field could be decoupled from the thermal field. And then we would get on into a loop that would calculate the magnetic field and the temperature fields of the solid and fluid domains in a coupled manner, and that would be for the code name DNS AMR foam. If we prove that the magnetic field could be decoupled from the temperature field, then I developed another solver for that would be named decoupled AMR foam, and it would substitute that red square you see in the flowchart by a subroutine that would read the magnetic field from a file too. And then we would end the time step by updating the temperature of the heat exchangers and calculating some other integral values. So then I had to prove the correct resolution of the thermodynamic cycle, and for that I chose to reproduce the experiments by Ball et al. On a parallel plate regenerator that was made of 13 plates, and it had a porosity of about 0.3. But first of all, I wanted to check if the magnetic field resolution could be decoupled from the temperature field of the solid phase. And well, for that, I chose to simulate a single magnetization step on a regenerator that started with a linear temperature gradient between 280 and 310 kelvins, and the applied magnetic field was 1 Tesla. I also chose to turn off the thermal conductivity of the solid phase to see the maximum difference between both solvers, DNS AMR foam and decoupled AMR foam. And well, the difference is plotted in that graph on the right, and you can see that the maximum is about 0.25 kelvins, which is less than the accuracy we expect from the magnetocaloric effect. So we can safely assume that the magnetic field would be indeed decoupled from the thermal field of the solid phase. So on this slide you can see the solution of the regenerator. On the left would be the temperature span of the regenerator at zero cooling load plotted against the fluid displacement of the fluid surges. And on the right would be the temperature profile of the regenerator for a 50% fluid displacement. And so on the left you can see how the solution is plotted for 3 cases. With the circles would be the solution given by decoupled AMR foam. Then with the squares would be the measurements by Ball et al. And with the rhombs would be the solution given by a 2-dimensional solver produced by the same authors that did the experiments. And well, they give 3 reasons why they observed those discrepancies. First one would be impurities in the magnetocaloric material, in gadolinium. A second one would be the lack of modeling of the heat losses to the environment, which I didn't include either. So to me, the most compelling argument for that discrepancy would be the third one, would be a simplified representation of the magnetic field. I applied an instantaneous and homogeneous magnetic field on those plates. So I think the following slide further proves the importance of correctly modeling the magnetic field in the regenerators. And well, we can see the evolution of the temperature span of the regenerator as we go increasing the ratio between magnetization and surge time. As we go increasing this ratio, the heat transfer fluid is at rest more time at extreme points of the regenerator that have a larger temperature difference with the ambient, so it is logical to think that the heat losses would increase as we go increasing this ratio. And effectively we see how the discrepancies between decoupled AMR foam and the measurements increase by increasing this ratio, which tells us that probably the heat losses were not such a prominent phenomena at lower magnetization to surge time ratios. So now that we can accurately compute the dynamics of a magnetic regenerator, we can start thinking which kind of numerical experiments we might want to perform with it to check what are the influences of different geometrical parameters on the performance of these regenerators. But first of all, I'd like to introduce you to what has already been done in the literature. And well, Apre et al. Concluded from a one-dimensional numerical model how longer and narrower regenerators suffer less from conduction losses, but more from viscous losses. Then Nielsen et al. Showed that with the help of 2-dimensional numerical models of plate regenerators, how if they lowered the porosity of these regenerators, the number of predicted transfer units would be higher because more heat would make it to the fluid phase, and that would increase the cooling power and the temperature span of the machine. However, if they operated at a higher frequencies, the predicted number of transfer units would be lower because the surge time would be reduced. However, because they were making more cycles per second, the cooling power and the temperature span of the machine had an increase. Tusek et al. Explored through one-dimensional numerical models, which would be the effects of changing the diameter of the particles of a packed bed regenerator, and they showed how if we reduce the diameter of those particles, the heat transfer surface of those regenerators would increase, and then we could increase the heat rate that would make it to the fluid phase, and that would increase the cooling power of the machine. However, for higher frequencies of operation, the optimum particle diameter would increase to keep at bay the viscous losses of the machine, and thus a higher coefficient of performance. They all perform several simulations on a one-dimensional model that included different geometries, and that would include packed bed regenerators, regenerators made of microchannels, parallel plates, and stacked wire meshes. So through the results we can see how for geometries that had a reduced heat transfer surface, the optimum coefficient of performance was reached at lower frequencies because, well, the geometry needed more time to transfer the heat to the fluid phase. And to reduce the solid conduction losses, as Aprea et al. Pointed out, the optimum geometry of the regenerator would be longer and narrower. Then Trevizzoli et al. Experimentally measured different geometries of a regenerator that had a similar magnetocaloric mass and regenerator volume. So the results were comparable between each other. And well, they concluded that the regenerator made of square pins had a similar performance to the packed bed regenerator. And they concluded, like other authors in the past, that packed beds trade efficiency for a higher cooling power. As I have explained earlier too, the geometry of the regenerator highly influences the perceived magnetic field. So the effort has been to approximate that demagnetization constant I talked about earlier. And so Aroni provided an average value for that demagnetization constant for rectangular prisms. And then Pozarov and Kogan more recently provided more average values for different geometries like cylinders, cones, and pyramids. However, what we're really interested in for the simulation of magnetic regenerators would be the demagnetization of clusters of particles, because we have a porous structure in the regenerator. So Martinez Huerta et al. Provided an approximation for clusters of particles of high porosity, and they analytically obtained that approximation and then experimentally validated it. And the approximation is rather simple. The total demagnetization would be a summation of the self-demagnetization and the dipolar interaction between those particles. And at the same time, the dipolar interaction would be proportional to the porosity of those clusters and the difference between the total demagnetization of the macroscopic shape of the regenerator and the self-demagnetization of those particles. Bjork and Bolt went further to test this approximation on geometries that are closer to a magnetic regenerator, and that would be randomly packed beds of spheres with a lower porosity. That would be 0.3 more or less. And well, they found out that their simulations were acceptably close to that approximation, and that the demagnetization constant is a function as well of the relative magnetic permeability of the material. Christensen et al. Performed a similar study on stacks of parallel plates. They did not compare their results to the approximation provided by Martinez Huerta. However, their results followed the same logic. So the design objective of the geometry of these magnetic regenerators can be summarized by the trade-off you see on the upper side of this slide. We would like to use the minimum amount of magnetocaloric material at the smallest as possible volume to be magnetized. However, we would like to extract the maximum cooling power we can at a reasonable temperature span. So I decided to simulate the operation of regenerators made out of pins with the cross-sections you see on the right side of this slide. So the novelty of this study would be centered in using a three-dimensional direct numerical simulation for the simulation of the magnetic regenerator. And I consider a new parameter that has been mostly ignored in the literature, that would be the tortuosity of the fluid flow. This is related to the distance the heat transfer fluid has to travel to make it to the other end of the regenerator. And I consider pin geometries because they have an easy axis of magnetization, and since they don't have to be in contact with each other, that might reduce as well the conduction heat losses. So I consider two configurations for these pin geometries, and that would be staggered and straight cases, as you can see on the upper side of this slide. And I thought as well that it would be a good idea to try to represent as close as possible a magnetic field that is present in rotatory prototypes. So I decided to place the regenerator in question, as you can see on the lower part of this slide, in the middle of two halves of the same regenerator, and those were connected to each other by periodic boundary conditions. That way I could take into account the influence of these neighboring regenerators. So the height of the pins was 4 millimeters for all cases, and the curvature effects of the wheel of regenerators was neglected because the radius of that wheel was hypothesized to be much larger than the height of those pins. In all cases, the mass of the magnetocaloric material was kept constant, and thus for the cases of constant porosity, the volume of the regenerator was constant as well. The applied magnetic field was 1 Tesla at the poles of the magnet, and the time of fluid surges and magnetization was kept equal as a characteristic of rotatory regenerators. And well, the width and length of those regenerators was limited by the computational resources available, and you can see some of those dimensions in the following table. So I thought it was a good idea to analyze the physical phenomena separately on those geometries to try to figure out why some regenerators might outperform others. And so I started with the demagnetizations of those clusters of pins, and as you can see on the table on the upper side of the slide, the self-demagnetization does not change considerably for the different outlines of the pins. Then on the lower side we have that the simulations of those clusters of different porosities are pretty close to the approximation given by Martinez Huerta et al., and they only start to present some discrepancies the lower it is their porosity. So all in all, the lower it is the porosity, the higher is going to be the demagnetization of those geometries. Then I went on to calculate the fluid flow through those geometries, and on the left you can see the tortuosity of the staggered cases computed as an average of 1,000 streamlines. The straight cases had a negligible tortuosity. And on the right side you can see the pressure head of those geometries. And especially for the lower porosity cases, the difference between the straight and staggered cases is higher, the higher it is the tortuosity of those geometries. And this is especially true for the case of the highest tortuosity of them all, which has a pretty remarkable tortuosity compared to other cases, and that would be for the staggered plates. So I wanted to evaluate as well which would be the heat transfer between the solid and fluid phases of those geometries, and for that I ran simulations that start with a temperature gradient of 2 kelvins in those regenerators and an additional 1.5 kelvins for the solid phase, and with that I tried to mimic the magnetocaloric effect. So these simulations had two stages. In the first stage they ran for 250 milliseconds with no fluid flow, and in the second one the heat transfer fluid was flowing for another 250 milliseconds. So what you see here on the graphs is the evolution of the Nusselt number for that second stage of the simulations where the fluid flow is running, and you can appreciate how the geometries that had an increased amount of tortuosity like circles or squares and staggered plates had an increased Nusselt number on that second stage of the simulation. So this larger pressure head and Nusselt number for the staggered cases or the larger tortuosity cases comes from an increase in the local velocity of the heat transfer fluid. Since we're keeping constant the mass flow of those surges and the tortuosity is higher, so the distance that the fluid has to travel is larger, the local velocity has to increase. This is exemplified in the left side of the slide. So on the right side you can see another simulation of the thermal field, and in this case I wanted to calculate the generated entropy by conduction. And for that I initialized the regenerators with an initial temperature gradient of 2 kelvins and with no additional temperature for the solid. And then I ran the simulation with no flow for 250 milliseconds. Most of the geometries didn't show a prominent change between the higher tortuosity cases, except for the one that showed the biggest change in tortuosity of them all. That would be the case between the straight and staggered plates. We can see how the generated entropy by conduction really decreases. And well, this comes from the way in which you have to arrange the magnetocaloric material to increase the tortuosity. We have to intercalate many times the heat transfer fluid and the magnetocaloric material, and well, that reduces the temperature gradient that the magnetocaloric material is going to perceive. So finally I present you the solution of the thermodynamic cycles of the last three geometries we have seen in the last slide. That would be red for staggered plates, green for staggered circles, and blue for straight plates. And the last two, staggered circles and straight plates, they follow what we have seen in the literature. As we go increasing the porosity of those cases, the decrease of the Nusselt number in those cases overwhelms the positive effect of reducing the demagnetization losses and the conduction losses of higher porosity cases. However, for the case of staggered plates, we see that they already have the highest temperature span of them all, and that would come from the reduced conduction losses that they presented earlier. And we see an inverse trend. So as we go increasing the porosity of the staggered plates, the temperature span of the regenerator increases. That means that the Nusselt number is not so affected by the increase in the porosity due to an increase of the local velocity of the fluid flow due to the higher tortuosity of the staggered plates. The conclusions of this project can be summarized in the following slide. One-dimensional models have proven to be somewhat limited because of the amount of models we need to plug into them, and because of the accuracy of those models can be somewhat limited as well. The insulator layers have proven to reduce the conduction losses effectively and improve the performance of plate regenerators. The accurate three-dimensional numerical simulation of magnetic regenerators has proven possible, and the calculation of the fluid velocity profiles and the magnetic fields has also proven to be decoupled from the thermal field, which is great news because the computational load that the solution requires has been lowered substantially. In terms of demagnetization, the outlines of the pins that were simulated did not influence too much in the total demagnetization of the regenerator, which means that the demagnetization of the regenerator will be mostly determined by the porosity. And well, the approximation of Martinez-Huerta et al. Proved to be adequate as well for higher porosity cases. The higher tortuosity cases show an increase in the pressure head and nozzle number of the fluid surges, and a reduction in the conduction losses of the regenerator because of the way in which we have to arrange the magnetocaloric material to increase the tortuosity of those geometries. So I would propose a new strategy for designing future regenerators, and that would be, instead of increasing the heat transfer surface of those regenerators, that would be increasing the tortuosity. That way, instead of increasing the heat transfer between solid and fluid phases at all moments, so at all moments would mean demagnetization and fluid surges, we would increase only the heat transfer at surge processes, which would bring our cycle closer to a Brighton-like cycle. So the future research on magnetic regenerators could focus on the following points. Getting a richer library of magnetocaloric materials would benefit the simulation of multi-material regenerators, and well, these are thought to be the easiest way to increase the cooling power of these machines, because well, we could optimize the Curie temperature of the regenerator for the different points in the temperature span of the machine. Then simulations of higher tortuosity and lower heat transfer surfaces would be easier to simulate because of the reduced geometrical details of a reduced heat transfer surface, and that would mean a lower computational cost of these simulations. So the proposition I made earlier in the last slide of increasing the tortuosity of the fluid surges, I think is similar to the proposition made by Kitanovsky et al. In their book of introducing Peltier devices to control the heat transfer between the solid and fluid phases. Well, in this case, we would be using the Nusselt number to control the heat transfer of the regenerator between the surges and the demagnetization processes. We could investigate as well the surge times of these cycles to try to approximate them to a Brighton cycle. And we could adapt this three-dimensional model that I presented to other alternative refrigeration systems like elastocaloric or valorocaloric or electrocaloric systems by just implementing the resolution of the new physical field that drives this phenomena. So that was all. Thank you for your attention, and to the industrial partners for their support. If you want any further information, please visit the references are included here, or leave a comment. I will try to answer it. Bye.